All right, so in this chapter, we'll talk about integral function. Integral, because we've already discussed what a derivative of functions. For integral of a function, we will start with what we know as the antiderivative, right? So I'll give a definition for an antiderivative. Because we already know what a derivative is. The definition for antiderivatives is if you have a function, then we say that this is an antiderivative. It's an antiderivative of the function f if the derivative of this big F is equal to f of x. Example, if you have f of s as big of this is equal to s squared, say it's an antiderivative. It's an antiderivative of f of s, which is equal to 2s. Since we know that f prime s is equal to 2s, which is the same quantity. So the antiderivative just means if you have a big F function, which is an antiderivative of another function, small f, if the small f function is equal to the derivative of the big F function. So you can see from here that we can write for the same function f, we can have for the same function f, we can have several antiderivatives, right? So example, we have several antiderivatives, right? Several antiderivatives exist for f. Example, if we take f, big F of s to be x squared, then its derivative, right, is 2s, which is the same as f of s. But then 2, if we take big F of s to be x squared plus c, then again the derivative, right, is equal to 2s. And then again, if we take big F of s, then this is s squared minus c, which is f prime of s, which is 2s, which is f of s. So for f of x is s squared, we have the f prime to be 2x. For f of x is equal to s squared plus c, we have the f prime is 2x, and so on and so forth. So you can see that in general, we can write, for instance, we can write if we have, let me say, if not c, maybe plus, maybe I can write here so that I can write a generalize. So I should say plus 100, and this is minus 100, for instance, right? Then we still get the derivative to be 2x, right? So in general, if c is a constant, right,
is a real constant, a real number and a constant, then s squared plus c, right, is an antiderivative of 2s. Okay. And then the process of finding all these antiderivatives, of finding antiderivatives, right? It's called antidifferentiation. So the process of finding all these antiderivatives is called anti-differentiation, right? So it's very, very, very powerful because, but the thing is that it means that if I give you f of s to be x cubed, then you should find f prime of s, which is equal to f of s small f, right? Which is 3x squared. Right? Then with that, we can have, with that, we know that for integrals, we can have as 6.1 is such an indefinite so indefinite integrals we usually write integral of a function f of s. S should give us f of s plus c. Right? Of course, we already said this f of s is equal to the big F prime. And then this c here is arbitrary constant. We call this one, we call this guy here the integral sign. And we call f of s ds as the indefinite integral. Okay, so the expression f of s, the expression f of s here, we call this the integral. And then we say that we have indefinite integration is the process of finding this big F f of s plus c. Given fs ds. For example, if you are given an integral of 3x squared to x, you ask yourself, the question you ask yourself is that this 3x, right? This 3x that we are given 3x squared. What you are seeking for is what function do you differentiate to get 3x squared, right? So in that sense, you know that if you differentiate x cubed, you get 3x squared. Right, so that's how you have to think about this anti-differentiation. Then if you have cos x dx, you ask yourself, what function do you differentiate to get cos x? So you know it's sine x, right? Because of this that we are using, which is the same as the derivative of f of x dx is equal to f of x plus. So the derivative is given under the integral sign, and the function itself is given as the result. Right? So if you do that, then you see that it becomes a bit laborious, because if I give you an integral, right? If I give you any integration, maybe x minus 3 dx, you have to find what function do I integrate or do I differentiate to get something like this, right? And you may have to think of something like 1/2x squared plus c. So it becomes a bit complicated thinking of what functions we have to differentiate to get the solution. So there are the basic rules, right? There are some basic integration rules, right? Or integration functions. Basic integration functions that one can easily learn. For instance, if you have a constant and then you find an integral, then you should get the constant times an integral plus c. If you have a polynomial x to the power n, then this is n x, this is x to the power n plus 1 over n plus 1, right, plus c. Okay, then we have other ones like the integral of cos x dx is sine x plus c. We also have the integral of sine x dx is also equal to minus cos x plus c. We have other ones, the integral of sec squared dx is equal to tan x plus c. We have the integral of e to the power x dx is equal to e to the power x plus c. We have other special ones. The integral of 1 over x dx is equal to x plus c, and so on and so forth. So these are basic integration functions that one must be able to identify them easily. So example, if I give you x to the power 9 dx, right? Then you know for sure that you have to use one of the integration properties, the polynomial. So it says x 9 plus 1 over 9 plus 1 plus c, and this is x to the power 10 over 10 plus c. So this is a typical example of how to tackle or how to apply this. So let me say this is 1, maybe for 2, the integral of maybe
5. Let me write integral of cube root of x squared x. So here you write integral of 2/3 dx, and this is the same as x 2/3 plus 1/2/3 plus. And then you have x to the power 5/3 all over 5/3, and this becomes 3/5 x 5/3 plus c. Right? So this is how you do, but just by applying the same rules as the basic integration of functions, basic ideas of the basic integration functions, to be able to solve as many integration problems as possible. Okay, then there are certain important properties, right? Properties of indefinite integral. These are properties of indefinite. Right. One is that the integral of a constant function f of x is the same as a constant times the integral of f of x, right? Where the constant is not 0. 2, the integral of the sum f of s plus or minus g of s is equal to the integral of f of s plus or minus the integral of g of s ds. So example is that if you have the integral of 5x cubed plus 2 cos x dx, then this you can write it as 5 integral of x cubed dx plus 2 integral of cos x s, and 5 is a constant. Here we have x 3 plus 1 over 3 plus 1 plus 2. The integral of cos we said was sine x plus c, and this you can write it as 5/4 x to the power 4 plus 2 sine x plus c. Of course, you can take another example. You have the integral of 8x cubed minus 6 square root of x plus 1/x cubed dx, right? This you can write it as q dx minus 6 square root of x dx plus 1/x cubed dx. Okay, so now in this case again, now you have 8x 3 plus 1 over 3 plus 1 minus 6, right? This is x half plus 1 over half plus 1 plus, so this is minus 1 over 3x squared plus c.
right? Sorry, 1/2 x squared. 3x squared plus c. And then this will finally become 8x to the power 4 minus 4x which will become 2x to the power 4 minus 4x raised to the power 2 minus 2x squared. Then, of course, because of what we have the definite integral. The definite integral. So for the indefinite integral, we said that the integral of the function to x will give us an f of x plus c. For the definite integral, as the name really rightly suggests, it's a definite integral between points, right? So if I write integral of f of a, integral a to b, f of x to s, then usually you can write this as big F of a and then minus big F of b. And this is rightly known, right? This is rightly known as fundamental theorem. Okay, a lot of fun. So this is rightly known as a fundamental theorem. Where f is continuous on the interval a and b. And this is an antiderivative. F on the interval. So sometimes people write in different ways. So this A, B, F of X. Sometimes people write it as F of X, A to B. Sometimes as well in some books, some authors also write F of S. X is equal to A to B, right? In this case, in that case, A and B have a name. So A, we call it the lower limits. The lower limits, right? The lower limits of integration. Right? The lower limit of integral, and B is the upper limits, right, of the integral. So, example is if you have 1 to 2 of x squared dx, then this you will get s cubed, right? S cubed over 3, 1 to 2, and this will be 2 to the power 3 over 3 minus 1 to the power 3 over 3. This is 8 over 3 minus 1 over 3. This is 7 over 3. So this is how the indefinite integral goes. Another example, minus 1, 2 of a function like 5x squared to x.
and this will become 5 minus 1 to 2 x squared to x. This will be 5 x squared is x cubed over 3 minus 1 to 2. And then you can have 5 over 3, 2 to the power 3, minus 5 over 3, minus 1 to the power 3. So this is 21 over 3. Sorry, this is 30. This so this is 5 times 8 is 40, right? Minus 5 over 3. So this is 40 over 3. That's 5 over 3. This is 45 over 3, which is 1 and 50. Of course, there are times when we need to do change of variables similar to what we did, right, for the differentiation, right? So if I call this first one, then I can call it, I can do the indefinite integral. Change of variables, because your integration can be very complex, right? So usually if you have function like that, 5x plus 7, right, ds, or if you have another one, cos 4n ds. If you have these kind of functions, then it's possible then it's straightforward. We cannot use, so we cannot use, right? Not use directly the basic, right? The basic integration formulas, integration functions. So in such an instance, we do substitution, right? Substitution. So what does it mean? It means that you choose a function, you choose a term, and then you substitute it to be able to derive finally your answer. So example, if you have the integral like this, 5x plus 3 dx, what do? You start by choosing a substitute, right? So say let u, for instance, let u, right, be equal to 5x plus 3, right? If you do that, then now you can find the u, the x to be equal to 5, and then the u over 5 is equal to the s. Okay? So now you go back again to your original function and substitute your u and then the dx. So now your original function, which was 5x plus 3 dx, we know that 5x plus 3 is u, and then dx we also know as du over 5. So finally we have 1 over 5 integral square root of u du, and we can solve this finally to be 1 over 5, 1 over 5, right? Then you have u half plus 1 over half plus 1 plus c. So this is 1 over 5 times
2 over 3 u 3 over 2 plus c. This is 2 over 15 u 3 over 2 plus c. But we know that u is nothing else but 5x plus 3 to the power 3 over 2 plus c. So you see, you can just make a substitution that then makes you be able to apply the basic integration rules. Okay. So if we take another example 2, another example where we find the integral s squared minus 1 to s cubed minus 3s plus 1 to the power 6. Here, what do? You start by saying let u be equal to x, right? Cubed minus 3x plus 1. Then du dx will be 3x squared minus 3. And this will be the same as 3s squared minus 1. So your du over 3 is equal to x squared minus 1 gs. Then we can go and substitute. So we have an s squared minus 1 gs over s cubed minus 3x plus 1 to the power 6. So now we can write the integral integration in terms of u. So the numerator, you can see s squared minus 1 dx is the same as du d3 over 3, right? So this is du over 3. And then the denominator, that was equal to u. So this is nothing but 1 over 3 integral du over u. And this is nothing else. Sorry, this is the power 6. The power 6, right? So this is the same as 1 over 3 integral u minus 6 du. And with that, you'll be able to get 1 over 3 minus times u to the power minus 5 over 5 plus c, and this will be 1 minus 1 over 15 u to the power 5 plus c. Of course, we know what u is, right? So it's 15 s cubed minus 3x plus 1 plus c to the power 5. So these are how we do the substitution for the indefinite integral. Of course, it's possible to also we can do maybe 1, 2 more examples. So an example, let's take integral e to the power square root s square root of s. Then let's take u to the square root of s. Of course, this is the same as s to the power half. And then let's do the u to s to be half s minus half. So this is 1 over 2 square root of x. Right? So your du that you want to separate will now be 2 times du is equal to the x over square root of x. Because we've written in such a way that we are able to make direct substitutions in our integration as well. So e to the power square root of s over square root of s ds, we can now write it as now e to the power, we know square root of s we said was u, right? And then the other part, which is the ds over square root of s, the other part here, we know is coming from this part here. So square root of ds over square root of u s is equal to 2 du.
is equal to 2d. So finally, we can write 2 integral e to the power u du, and this will be 2 eu plus c. Of course, we know u is square root of s plus c. So all these are part of the how to do the change of variables for indefinite. Of course, when we want to do definite, right? For definite integral, what we do is that if we choose a substitution, then we also need to use that substitution to change the limits of the integrals, right? So for instance, if we write 2 to 10, 3 over 5s minus 1 s, and then you choose u to be 5s minus 1, such that du ds is equal to 5, and then we have ds will then be du over 5. But then we need to change to 1. Then we also need to use the substitution that we have to also change up the limits of integration, right? So 2, I say now change the limits, right, of integration. The limits. What does it mean? The limits of integration changing. Now you take u and you say, okay, u x is 10, so 5 times 10 minus 1, and this is 50 minus 1, this is 49, and then the other one is u of 2, which is 5 of 2 minus 1, which is 10 minus 1, which is 49. So now we can rewrite our whole equation 2 to 10, 3ds over square root of 5s minus 1 to be equal to 9 to 49, right? Then now we have 3 over, now we have square root of u, right? And dx is equal to du. So altogether we have 3 over 5 integral 9 to 49, right? U to the power minus half. And we can solve that. We can solve that. We're saying it's equal to 3 over 5, right? U to the power half times 2, right? Well, let me make correction there. Over half, right? From 9 to 14. And this will be the same as 6 over 5 square root of u 9 to 14. And this is 6 over 5 square root of 49 minus 6 over 5 square root of 9. So this is 6 over 5 square root of 49 is 7 minus 6 over 5 square root of 49 of 9 is 3. And this will give us then 42 over 5 minus 18 over 5, and this is 24 over 5. So that's for the indefinite. Then the next part that I want to also address
is the issue of applications, right? Applications. So applications of integration. So here, we say that if you have, so we can use integration to find, right? To find, so to find the equation of a curve. That means giving example, right? If you are given the gradient, you are given the gradient of a curve, that is usually dy ds or f prime of s. The equation of the curve is obtained via integration. Right? So if you have dy dx is equal to some f of s, then y is the integral of f of s. That's what we mean to find the equation of the curve. Right? So example, if a curve passes through, the curve passes through points 1, 0 and its gradients at any point. P x y is 3x squared minus 1. Then we can say find, let's find the equation. Find the equation of curve. So in such an instance, you know that dy dx, right? Dy dx is given as 3x squared minus 1. So for sure, y is equal to the integral 3x squared minus 1 s. And this is equal to s squared minus s plus c. But we know that the curve goes through a certain point 1, 0, right? We know that the curve goes through a certain point here, and this point is 1, 0. So it means at x is 1, y is 0. So we can substitute that into our equation of the curve to find c, right? So to find c, substitute, right? Substitute the point 1, 0 into the curve. That means y is 0 means x is 1 cubed minus 1 plus c. This is equal to c. So it means it implies that c is 0. And your equation of the curve is s cubed minus x. So we can use it to find the equation of the curve. We can use it to find other parameters. If you are given acceleration, you can find velocity or distance. If you are given so all these things, you can use it. You can use it to find these properties. Then the second one is the area under a curve. Area under and between curves, right? So area under and between curves also means that, for instance, if you have a curve so for instance, we have curves, we have curves y is equal to s, and you can find the area under such a curve of the point x is equal to a, point x is equal to b. And then the area in such an instance is given by a to b of the curve f of x. Right? So example, you can say find the area, right, under the curve, of a function f of s is equal to 7 minus s squared within the interval, right? Within the interval x is equal to -1 to x is equal to 2. Right? So solution is that your function f of x is 7 minus s squared. Your x is between 1 and 2. So your area is from -1 to 2 of your function, which is 7 minus x squared to s. And then you can easily do this because this is 7x, right, minus s cubed over 3 from -1 to 2. So what do? You take 7 times 2 minus 2 cubed over 3 minus 7 times -1 minus -1 cubed over 3. Right? So this will give us 14 minus 8 over 3 minus -7 plus 1 over 3. So 14 minus 8 over 3, that gives us 11, 1 over 3. So this is 33, 34 over 3. And then this one is to give us 20 over 3. Which all together should sum up to altogether. So I write the sum. Right, to give us 54 over 3. And that is the area under the curve, for instance. And then we can take another example, area between curves, right? So when you have two functions, right? When you have f of s, when you have f of s to be bigger, right? When you have f of s to be greater or bigger than g of x, then the area between two curves, for instance, area between two curves, where this curve here is f of s, and then this curve here is g of s. Then we can find the area between these two curves. So in such an instance, the area between these two curves, if we have from A to B, is from A to B, and then it is also from f of s minus f of s to s. So, for example, we can find, right, we can find the area between two curves. F of s to be minus s squared plus s plus 6, and g of x to be s squared minus 5s. Well, within the interval s is 0 to 3. Solution. How do we find the area in such an instance? So in such an instance, we know so the blue part, right? The blue line is greater than the. If you plot this as well, if you plot this equation or these two functions, you have something like that. This point is 3, this point is 0. Then you will have, so, and then this is equal to the f of s. And then you have another one like this. I'm going to bring it over here. And this one is equal to g. And you're asked to find the area between them. So again, your area is now from 0 to 3. And your f of s is minus s squared plus s plus 6, right? Minus your g of x, right? Your g of x is s squared minus 5s plus 6 ds. So now 0 to 3, and now you have minus s squared, right? Let me use another color. So you have minus s squared plus x plus 6 minus s squared plus 5s minus 6 ds. So if you do that, then you have 0 to 3. Then you have minus, so you have minus 2x squared. Then you have plus 6x dx. And then finally, you have minus 2 over 3 s cubed plus 3x squared from 0 to 3. And this basically means minus 2 over 3 to the power 3 minus 3 times 3 to the power 2. And if you punch your calculator in, you have 9. So it's of course we are able to also do the integration along the y-axis. So if you have a curve, like that, which is x is equal to f of y, and then you have another curve like this, which is x is equal to g of y, where the integration is a to b, then the area in such a case is from a to b, but now it's going to be fy minus jy along the y-axis, right? Also, in some instances, we have that you have a curve, that's function like this, and another function like that, where y is equal to g of x, and in this case, y is equal to x. And we have a to b, but they also meet here, so we call it a c. We are asked to find the area of this curve. Of course, in such an instance, you need to write your integral from a to c, and within a to c, f is greater, right? So if you are here in this part, f of x is greater than g of x, and then in this part, g of x is greater than f. So here in the first part, A to C, you write f of x minus g of x dx, then plus the second part, which is C to B, and then now you write g of x minus f of x dx. Well, similarly, it can also be done along the y-axis as well, similar to what we discussed already. Okay, and then of course the easiest one as well is that sometimes you are given a curve like that, where you have this here, where you have then the C, for your B and the B for your graph. Equal to y. F is equal to f of y. Let me so now x is equal to f of y, and in that case, of course, your area is a to b, right? F of y dy. But that's not all. With that, we'll talk about some properties of the integral, which is very, very important, so that you understand how some of these things come about. So, for instance, if you have an integral function, if you have so finally I'll end with the properties. Some properties of integrals that you should know. That one, the integral of f of a function from a to b f of x dx is the same as the negative from b to a f of x dx. Two, the integral from a to a of f of x dx is 0. And 3, which is some of the properties we have used, that a to b f of x the x. You can call it the integral splitting, which you can do for a to c, f of x ds plus c to b, f of s ds as well. And some of the other properties, we already discussed them, as in the sum, the integral, the linearity, the integral of the sum is the sum of the individual integrals as well. And then we also discussed the constants, integral of a constant as well. So yeah, with that, we'll end the part on integration, and we'll continue next from parameterization and parametric equations. Okay, then finally, one part that wanted to talk about is the absolute value integration. So if you want to find the integral of an absolute value, you can always write, the absolute value, you write it as x and minus x, for x positive and for x negative. And so you can rewrite the absolute value in that sense as well. And then you can use it to solve an equation. All right, so we'll stop here.